I went to Professor Waltier's lecture where he explained why the future was paved in epigraphene, and specifically, he discussed how graphene is a novel form of 2D carbon atoms that have amazing material properties. He discussed the future of graphene and how it could be used to manufacture batteries and electronics and would change the rules for what is possible in the future. And he started out by discussing some background on graphene and discussing how it's a single sheet layer of carbon that is derived from graphite, and that specifically graphene has very weak bonds between the sheets. In graphite, the bonds that pull the sheets together are the strongest bonds horizontally, but the vertical bonding is virtually absent. And he discussed how there's very little difference between graphene and graphite. Graphene was discovered by a German chemist named Bohm in 1962. And eventually various forms of graphene were discovered, including chemically exfoliated, CVD graphene, mechanically exfoliated, epigraphene, which is what he mainly talked about, and then graphene deposited on a silicon wafer. He also discussed Henry J. Round, who was the first inventor of the first LED in 1907 using silicon carbide. And he discussed Axen, who synthesized silicon carbide and graphite to produce ectaxial graphene. And what he found was that when silicon carbide like crystals are heated, silicon evaporates ultimately, covering the surfaces with high purity graphene, which turned out to be epigraphene. Specifically, like I said, epigraphene is graphene that is grown on SiC, which is silicon carbide. The way that this was discovered was that it was put in a chamber and heated really high, and it was found that the silicon evaporated away from the silicon graphite, and the layers formed on the surface, which caused the layers of the graphene to atomically align. And if you were to compare epitaxial and exfoliated graphene, it was found that exfoliated graphene is not aligned with the substrate and can't be used for nanoelectronics, versus epitaxial was atomically smooth and aligned with substrate and is well suited for nanoelectronics fabrication. So then he discussed about how graphene has many benefits, including high electrical conductivity. It's 200 times stronger than steel. It's thin and very lightweight. It has high thermal conductivity, and it has very high transparency. And specifically, there's an enormous hype about graphene right now because nanoelectronics specifically is a very important application of graphene. He discussed how graphene was used in a variety of electronics, from the 1972 Intel processor to the 2019 Intel Core i9 processor. And then he talked about how any new material now must be complete with modern nanoprocessing. And that kind of paves the way for how electronics are functioning in the future. So this is where he discussed a roadmap of the use of graphene in electronics. So specifically, Epigraphene Electronics and the world's first graphene electronics proposal was founded in 2001 in things like ballistic devices, CVD growth, diffusion, and CVD growth on silicon carbide. The world's first graphene electronics funding was in Intel in 2003, and the world's first graphene electronics was presented in 2003 as well. Specifically, epigraphene electronics, and specifically in ballistic transport at room temperature, was a major breakthrough in this field. Graphene ribbons were grown on sidewalls of steps that were involved in SiC, and then nonpolar epigraphene also became very big when it was found that the edge state does not really have a Hall effect, and that a new kind of carrier might be involved in graphene. And the overall conclusion was that nonpolar epigraphene could be patterned using conventional microelectronics, which kind of paved the way for future electronics. So a few things that I learned from this lecture was what epigraphene was, because that's not something that I was aware of before, and specifically how it was formed, what the difference between epitaxial graphene was and related to epigraphene, and then how important epigraphene is for the future in terms of electronics, and how modern nanoprocessors have to have epigraphene involved in it in order to function. So it's really interesting to see that, and it was really interesting to see how this is going to evolve over time and follow that through.